All right, so we will go ahead and get into this next section of notes here. So this is a new unit, so if you have not already, make sure that you have a clean sheet of paper and you can label our next unit here. We're diving into Unit 8, and this whole unit is going to be about similarity. Okay, Unit 8, similarity. Okay, this one's going to be a little bit of a shorter unit. We'll only do 4 sections of notes on this. We won't have a quiz, or I'm sorry, we won't have a test for this unit. We'll just have a quiz at the end of those 4 lessons here. So starting off today, we're in 8.1, dealing with similar figures. Date today is either the 8th or the 9th, depending on what hour you have this class here. And we want to be able to find measures and variables of similar polygons. So diving right into it, what does that mean? Remember, we talked about the fact that a polygon is just really a shape. So the first definition here, similar polygons are 2 or more polygons. Okay, 2 or more polygons that have the same shape. Okay, they have the same shape, but are different sizes. Okay, they look the same, they have the same shape, but they're different sizes. So you're going to notice a lot of similarities between, no pun intended, between this unit and our congruence unit, because our congruence unit, we said there's 2 shapes that are exactly the same. Now we're talking about 2 shapes that are similar, are very close, but they might just be, one might just be larger than another. Okay, so for example here, let's take a simple one. Let's say we draw, let's draw a couple right triangles here. Draw one here and one here. Okay, we could say this one could be, for instance, let's say 6, 8, and 10. And then this one here would be, let's say 3, 4, and 5. Okay, this would be an example of 2 similar polygons. They look the exact same, or they're the same shape, they're oriented the same way. The only difference is the side lengths on one are larger than the side lengths on the other. Okay, one's just larger than the other in general. Okay, this is important because if 2 polygons are similar, then I can say something here, or I know some information. Okay, so if 2 polygons are similar, then the angles are all congruent, and the side lengths, or I should say the corresponding side lengths, are all proportional to each other. Okay, and we'll talk about what all that means in just a minute here, or we'll kind of practice that in a bit. But that is the basic idea, is all the angles are still going to be the same. The only difference is that the side lengths are going to be what we call proportional to each other. So again, little example here. We could have a couple different triangles. Let's say we'll go triangle ABC. We'll go ahead and label them this time. And let's say we have side lengths, or angles, excuse me, of all 60 degrees. We'll keep it simple. Say one triangle we have here is what we call equiangular. All the angles are the same. And then we know that means all the side lengths are going to be the same as well. Okay, and then we'll draw another triangle here. Try to make it look the same here, or at least close to it. Again, 60, 60, and 60 here. Equiangular. And this one we'll name DEF. Okay? And like we said, the angles are all going to be the same. The only difference is the side length. So for example, let's say one of the side lengths over here is 5, and one of the side lengths over here is 4. Okay, this would, again, would be an example of similar polygons. So this is the information that we can use and we can look for when we're trying to solve for different measurements here. Okay? And then one other thing that's going to be important is a similarity statement. It is very similar to some of the things that we saw before with a congruence statement here. So a similarity statement, we'll just say this. We're going to say it tells us which points are corresponding. Okay, that's all the similarity statement tells us, is it tells us which points are corresponding between 2 different similar shapes. So for example, if we're just using the two triangles that we just drew, I could say triangle ABC is similar to the other triangle, and our similarity symbol just looks like this. It's just a little squiggly line. So think of the congruence statement except without the equals. We just have the squiggly line here, and we can say triangle ABC is similar to triangle DEF. And just like we've seen before, that order is important. It tells us that A matches up with D, B matches up with E, and then C with F here. Okay, so pay attention to the order of the letters just like we did when we were talking about congruence. Okay, so with this being the case, let's practice this a little bit here. So you can take a sec and sketch those triangles here. But we have that triangle FGH is similar to triangle JKL, and I want to use the similarity statement to give properties or information about the angles and the side lengths here. Okay, so let's start with the angles because those are going to be a little bit easier. Starting with the angles. If we're thinking back to that property that we just wrote down, we said if these are similar, all the angles still have to be the same, and specifically the ones that are corresponding. So if I start with angle F, for instance, right here, angle F, I could say that that is still going to be congruent to the corresponding angle, which I see with the order of the letters is going to be J. So I could say angle F is congruent to angle J. Okay, that part has not changed from when we've worked through these kinds of problems before. Okay, and we can continue with that same idea. I can say angle G here is next. I'll go ahead and put two arcs around that. And just like before, if I look at the letters here, G is supposed to match up with K. So I could say G is congruent to angle K. And then same thing with the last pair of angles here. Angle H would have to be congruent to angle L as long as these triangles were similar. Okay, so we can use that. We know we can look for the corresponding angles and just set them equal to each other now. Okay, now with the sides, it's a little bit different. We had a different term that we said, where we said they're going to be proportional to one another. They're not necessarily going to be the same length. So just like before, let's just start off with one of our sides here. Let's say, for instance, we'll start off with FG. Okay, when it says proportional, it means I'm not going to be setting this congruent to another side length, but I want to set it up in a fraction. Okay, that's kind of what proportion kind of refers to. So for instance, if I look at the order of the letters here, FG would correspond to JK here. So I'm not going to mark a dash mark here because I don't want to say that they're congruent, but I'm going to put both of these in a fraction. And I'm going to say FG over JK. Okay, this would be an example of part of a proportion. It's basically just a fraction. Okay, what it means when it says it's proportional is it means if I set this equal to something, it's going to equal the same thing as if I set up fractions with the other remaining sides. So let's go with our next side here. Let's go with GH, and we know that corresponds to KL if we're looking at the order of the letters. And so this would be an example of a proportion. I would say whatever these lengths are, it doesn't really matter. They're not going to all be the same. But I would say whatever I would get when I took FG over JK, that would be the same thing as GH over KL. Okay, and then this also works for the last pair of sides as well. Okay, last pair of sides that I mentioned, FH. This would be the same thing as FH over JL here. Okay, so this is the new piece that we're going to be kind of practicing today and making sure we understand how to do, is setting up these proportions and then being able to use that and solve problems as well. Okay, so one other thing that we need to talk about that's going to be big in this unit is what we call a scale factor here. Okay, we're going to see this term or see this idea a good amount, so we want to make sure we understand what it's referring to. Okay, so the scale factor here is how much larger slash smaller. Okay, the scale factor is how much larger or smaller one similar shape is to another. Okay, it's telling us how much larger or how much smaller one shape is to another that is similar to it. So let's just use our example here. This time let's just draw a square since this works for any type of shape here. And since it's a square, let's say all the side lengths are 8, for instance. And then we'll draw a similar shape. So angles are going to be the same. The only thing that's going to change is the side lengths here. So we'll draw a similar square. And let's say on this one, all the side lengths are 4. Okay, don't need to worry about labeling them or anything like that. Okay, the idea behind this is if we were told that these two squares are similar, then my scale factor, if I go ahead and write this out, the way I get that is I just take one corresponding side over another. So for example, let's take the side on the left of this square, and that would be 8. And then the corresponding side in the other square, the good news is it doesn't really matter if we mess it up, but let's take the left side again, that's going to be 4. So my scale factor here is just 8 over 4, or if I simplify this fraction, that is just 2. And basically, like we said, this is telling us how much larger or smaller one shape is to another. So we're saying this big shape here is twice as big as this smaller shape right here. Okay, that is what the scale factor tells us. Okay, it tells us how much larger one shape is to another. Okay, so again, putting that into practice here. So look at these two trapezoids, or what looks like trapezoids here. We're told that ACDF is similar to VWYZ, so good to pay attention to the order of those letters because that'll tell us which points are supposed to line up. And then we want to use the scale factor to find X and find Y here. Okay, so first thing I need to do is I need to find the scale factor. And like I said, all we do to find that is we just take two corresponding sides and set them over one another. And here's the thing that we really need to pay attention to is I don't want any variables when I'm finding the scale factor. I want an actual number or an actual fraction to come out of it. I don't want to try to solve for my variables just yet. So if I'm looking at this picture here and I'm trying to find some different corresponding sides, I see, for instance, I have AF here. And if I'm looking at the order of my letters, AF matches up with VZ. So now I go look at my diagram and I see those two sides would be matching up. Okay, so I will use that information later, but the problem is, like I said earlier, I have a variable in here. And I'm not looking to have a variable, I'm looking for two sides that are just numbers and that are corresponding. So if I look at this other piece here, I see I have the side length of 9. We have this right here, I'll draw it this way. Okay, we have this side length of 9, and that's CD. And notice I see CD should match up with WY. So if I look at my picture here, these two sides would match up, and this would be the two sides that I need to set over one another. I would say 9 from the top trapezoid over 6 from the bottom trapezoid. Okay, so this would be my scale factor, 9 over 6. Okay, and if I wanted to, I could simplify this as well. It'll probably help us when we go to solve problems. So I'm going to simplify this here. This is the same thing as 3 over 2, if I'm simplifying that fraction. Okay, now that we have that, we can use that to solve for X and for Y. So if I'm looking for the side length with X, I see this right here, FD, and I see by the order of my letters that corresponds to this one right here, ZY. So here's how I'm going to set up my proportion, is I'm going to say here's my scale factor, 3 over 2, and that equals the same thing as those two sides over one another, which would be X over 10. Okay, so this is an example of a proportion. This is the way we use our scale factor, is we set it equal to two corresponding sides. And specifically, since 3 was on top up here, I needed to make sure X was on top when I wrote this proportion. Same thing with 2 and 10. 2 is on the bottom, and 10 was on the bottom as well. Okay, and now from here, there are multiple ways to solve these kinds of proportions. The first thing that you can look for is you can look for a number that you could multiply by to go from the left to the right. So for example, for here, and this only works for multiplication and division, don't try to add or subtract. Okay, but if I look at this here, to get from 2 to 10, I know I would just need to multiply by 5. Okay, that's good because now that means that's the same rule for the top. I have to multiply by 5 as well. So here I can just write this out. X equals just 3 times 5, so X equals 15 here. Okay, so that's one little quick thing that you can be looking for. If you know what number you need to multiply to go from the left to the right, make sure you do that. Again, don't do that with adding or subtracting. That does not work. Okay, so we solve for X. Now we want to solve for Y. And now we're going to go back to that proportion that I was talking about earlier. I'm still going to use the scale factor, 3 over 2. And then we see this right here, this expression with Y is 3y minus 1, and we already said that corresponds to 12. Okay, so I need to set those two over one another And again, I need to pay attention to which of those should go on top. In this case, 12 should go on top since it is in the top shape. And then on the bottom, I'm going to do 3y minus 1 here. Okay? On this one, if I'm trying to solve for the variable, I could try to do the same trick as before and look to see what I'm going to multiply to get from left to right. But I actually want to talk about one different strategy that's going to be used a lot in this chapter. Okay, one other thing, if this doesn't come out to be a whole number that I can find very easily to go from left to right, another idea that I can use is what's called cross multiplication. And so what that means is it means that anytime I multiply the ones that are across from each other or diagonal from each other, that's always going to equal the same thing. So for instance, these two that I've just circled being multiplied together is always going to equal the same thing as if I multiply the other two that are diagonal from each other. Okay, this will work, or these will equal out every single time. Okay, so we can use that now. So when I go to set this up, I'm going to multiply 3 times 3y minus 1. And so what I'm going to write this as is I'm going to write 3 on the outside, and then since 3y minus 1 is a whole algebra expression, I'm going to put that in parentheses all together. So 3 on the outside and then 3y minus 1. Anytime you do that, anytime you multiply by an algebra expression, or in other words, you have multiple terms other than just your variable, I would recommend putting that in parentheses. So we have this here, 3 times 3y minus 1, and then on the other side, I just have 2 times 12. Okay, since those are both numbers, I can just write that out, 2 times 12. Okay, and now we go to solve, and this is why I put this in parentheses, because it reminds me that I need to distribute that 3 to both terms. So I don't want to just multiply it by 3y, I also want to multiply the negative 1 as well. So 3 times 3y is 9y, 3 times negative 1 is negative 3, and then over here we have 24, because that's 2 times 12. And now we can just solve our algebra problem like we know how to do. I can add 3 to both sides. They cancel. I get 9y equals 27. Bring this last piece up here. So my last step here, divide by 9. And I end up getting y equals 27 divided by 9, which is 3. Okay? So those are the two methods that you can use to solve for your variables here. You're either looking for a number to go from the left to the right to multiply, or use cross multiplication. Okay? One more thing that we need to talk about for today is the perimeters of similar figures, okay, or a property that I have with the perimeters of similar figures. Okay? And what I can say is this, is the perimeters of similar figures will always have the same proportion as the scale factor. Okay, anytime I look at two similar shapes, if I'm thinking about their perimeters or what all the sides add up to, that is always going to have the same proportion as if I found my scale factor. Okay, so let's practice and show what that means here, because I know that has a lot of math terminology. So let's say we have this last one here. We have these two hexagons, and we're told from the start that RQPTS is similar to ABCDE. And what it's saying is I want to use the scale factor of these two shapes to find the perimeter of RQPTS, or in other words, the top hexagon. Okay? Well, first off, before I start solving this or trying to set this up here, I can go ahead and fill in some extra piece of information that I know just by looking at these diagrams here. Okay, so first thing that I know is I see I have 4 dash marks right here on RS, and I also have the same amount of dash marks on PT, which means these are going to be congruent. So if RS has a length of 3, that means PT is also going to have a length of 3 here. Okay, and then I can use that same idea down below. If I see AB has 1 dash mark, that means it's congruent to BC. So BC is also going to be 8. And then same thing down here, 2 dash marks, 2 dash marks. These would both have to be the same. They would both have to be 4. Okay, so notice I actually already have the perimeter of one of my shapes, or at least I could find it because I have all 5 sides here. But we'll use that in just a second. Okay, so now that I've done this, it says I want to use the scale factor. So I'm going to try to find the scale factor first. Always good to start with that. And in this case here, if I'm looking for my scale factor, I'm looking for 2 sides that are corresponding, and they're both numbers. So for instance here, if I look at this, I see I have a side length of 3 here. And if I look in the other hexagon, the one that would match up with that would be AE, or 4. So my scale factor is going to be 3 over 4. Okay, and the good news, some of you might be asking, does it matter if I put 4 over 3? It does not. Okay, the only thing that matters is when you go to set up the second proportion, you need to make sure that the points or the lines are matching up. Okay, so this is my scale factor here. It's 3 over 4, or in other words, the top hexagon is 3/4 the size of the bottom hexagon. And if I want to find the perimeter of the top one, I could use this individually and find the remaining sides, but I can do this a little bit quicker by setting the perimeters over one another. So what I can say is I can say 3 over 4 is the same thing as the perimeter of the top shape, so perimeter of RQPTS, over the perimeter of the bottom shape, ABCDE. Okay, this is what our property just told us. It says they're going to have the same proportion, one perimeter over the other, as the scale factor. Okay, I put RQPTS on top because when we found the scale factor, we put a side length from that shape on top as well. So those do match up. Okay, and then I can actually fill in some extra information here. So if I'm going to go write this again, let's say 3 over 4 here. On top, I have the perimeter of that top hexagon. We don't know that, and that's what we're looking for, so I'll go ahead and just label that X. Okay, it's an unknown number that we're going to try to find. And then on the bottom, the perimeter of ABCDE, I can actually find that because I have all the side lengths here. So the perimeter of ABCDE is just going to be 8 plus 8 plus 4 plus 6 plus 4. Okay, so I'm just going all the way around this shape here, adding all the sides together and seeing what I get. In this case, we can add these all together. That would be 16, 20, 26, and 30. So when I add all those together, I should get 30 here total. Okay, so what that means is I can go ahead and fill this in my proportion now. So 3 over 4 equals X over 30. And remember, X is going to be the perimeter of the big shape. And now, just like before, we have a couple different methods to solve. Okay, notice there's not a whole number that I can multiply 4 by to get to 30. So that's probably a good indication that it's easier here to do our cross multiplication trick. So I can multiply these two that are diagonal from each other, and that's always going to equal those two that are diagonal from each other. Okay, so the first two here, like I said, that's just 3 times 30, and that's always going to equal the other two being multiplied, 4 times x. Okay, and I can simplify these a little bit more. 3 times 30 is 90, and then 4 times x, that's not going to be a number, but we can just write it as 4x to keep it simpler. And again, if I gave you guys a problem like this, you should be able to solve this with algebra. Last step here would just be to divide by 4 to get x by itself. So I end up getting x equals 90 divided by 4. If we didn't know this, we could just type this into our calculator, or we could divide it by 2 twice, but in any case, it's going to come out to be 22.5. And so that will be our final answer here. What is the perimeter of that top hexagon? That is 22.5. Okay? And that would be, in my opinion, the quickest way that we could do that one. Okay, so that is the 8.1 notes. We do have a homework assignment that is with this as well. You should have either gotten that handed out in class or it's posted on the class website if you are not able to attend. And as always, if you guys have any questions, feel free to let me know. All right, thanks guys.